My last topic for new ones this year is the life around red giants. The example for anime that I used for this came from Macross Frontier, in which they visit this world, Gallia 4, which orbits a red giant, and they hang around there and they find plot devices on the surface and things like that. As you can see, there's some foliage going on down here, they got oceans up here, and apparently they're also orbiting a binary star system, just to throw in the sci-fi cliches. So, is this going to be possible? This was one that I didn't actually know what the result would probably be when I started out. And when I say that this panel takes me generally about 100 hours each year to prepare, usually it's only one topic that really just eats my soul in time. This was the one. I first started off kind of just trying to do it mathematically, and oh my god, was it horrible. So then I went about trying to read the research. I think I read close to 400 pages of research articles trying to sort this one out. Fortunately, I condensed it pretty well for you. So, just to kind of say some other things about sci-fi things where it pops up, Asimov, in his Foundation series, he had, I think it was Betelgeuse, the star in Orion that was the head of his Sirius sector, and Planet of the Apes takes place on another planet around a red giant. So it's something that pops up fairly often, so it's worth taking a look at, even if not for anime.
Planet Krypton.
Was that around a red giant?
Yep.
Okay, well there we go.
No, that here.
Yeah, it's not anymore. Now it's around something dead.
Just like Alderaan.
Just like Alderaan, very much so. But the star's still there. Well, what is a red giant? That's the first thing we kind of have to talk about. And to understand what a red giant is, you have to understand how stars live and die. So the first thing to kind of demonstrate that is this fun graph called an HR diagram, named for Hertzsprung and Russell, who were two astronomers back in the 1920s, who started by plotting up all the stars around the sun, comparing their temperature to how bright they are, and what they found out is that most of them lie along this line right here, which is now called the main sequence. And when we started figuring out what's actually going on, we learned that this is where stars spend most of their lives when they're burning hydrogen and making it into helium. But eventually in the core of the sun, or any other star, you're going to run out of hydrogen because you burned it all. So when that happens, the star is going to start dying. And when it starts dying, it no longer has the pressure to hold up all those outer layers, so the star starts contracting under its own gravity. And when you start squishing a gas, anybody that's taken high school chemistry can tell you it should get hotter. And it does. So the star actually gets hotter, even though it's ran out of fuel, and that causes a shell of hydrogen around the core to start fusing helium. And once that kicks on, now you have an extra source of energy pushing the star back out. So instead of just contracting, the star actually swells up again. And it swells up not just a little bit, but for a star like the sun, it is going to swell up about to the orbit of Mars. Which means in 5 billion years, when our sun runs out of hydrogen, we need to move. Earth is not going to be fun to live on because it will be inside the sun. So we don't want to live there. And just to kind of show what the evolutionary tracks look like, is it starts off here on the main sequence, and then they'll move off kind of the upper right as they start dying. The other thing is that stars evolve at different rates depending on how massive they are. The least massive stars evolve very slowly because they don't burn through the fuel very fast, and the massive stars do it very, very quickly. So these ones up here, these 100 mass solar stars, they may only live a couple 100 million years. The 1 solar mass stars, like our sun, will live a total of about 10 billion years. We're halfway done. So we got some time still. But the thing is that if we're going to talk about red giants, we can't do the really, really massive stars. You can't read it too well, but the ones way up there aren't giants. Those are super giants. So we're not going to talk about those. We want to limit it to the stars that can eventually become red giants. So that means the ones that are somewhere less than 5 times the mass of the sun during their main sequence lifetime. All right, so that's kind of covered what a red giant is. It's a bright star because it has a lot more surface area from being swollen up, and it's also very, very large. Now, we already said that you can't just have the Earth being, oh, nice and comfortable right now, we'll hang out for another 5 billion years and it'll still be comfortable. No, the sun's going to eat us. So we will either need to move, and if we do, we need to make sure that we have a nice habitable place to go to. Jupiter's not very habitable, but it has some moons that are actually fairly massive, that have thick atmospheres, not the kind we want to breathe, but we might be looking at doing something to them. So let's look at some of the other effects first. one of the things we're going to want for a planet is we want it to have a good temperature. We don't want to burn, we don't want to freeze. So we want it in a nice, comfy, preferably Florida temperature. I'd like that if I get to pick. But this is going to be affected by how much energy the star is going to put out. If you have a very, very hot star, you will have a very, very hot planet. It will also be affected by the distance of the planet, and it will also be affected by the atmosphere of the star, which we'll talk about in a second. But for any star, there's a range of habitable zones in there. And this is a recent diagram. Up at the top here, we have what it looks like for our solar system. We have Mercury here on the inside. It's not in the habitable zone. That's okay, it doesn't have an atmosphere anyway. We got Venus on the inside, which is just in the habitable zone, but it has so much CO2 and other stuff in its atmosphere that has a runaway greenhouse effect, and like I said, you can bake cookies by shoving them out the window. Earth, it's in the habitable zone. Unfortunately, we have an atmosphere that's right to be able to make it work even better. And Mars is also in the habitable zone, but it doesn't have a good atmosphere to trap the heat. So it could be, but it's not. Jupiter falls outside. And then down here, here's another recently kind of discovered planetary system of the now 500 other solar systems outside our own known. And it made big news because some of the planets were just falling in the habitable zone. I want to emphasize, though, that this is a habitable zone, and just like Venus and Mars, just being in the zone doesn't mean much. You also have to have the other factors. So we want to have this habitable zone, but since the star is going to be swelling up, as the star evolves and gets bigger, this is going to move out. So what we want to do is we want to find a place where we can hang out long enough that it's worth our time. So we need some other considerations here. So we already said that we need good temperature with the luminosity, but also the planetary atmosphere. Planetary atmosphere is also important because, as we've said before, I like to breathe. So if we look at these other planets right around ours, Venus is mostly carbon dioxide, 96.5%. Nitrogen, 3.5%. Oxygen doesn't even register. I don't want to breathe there. Meanwhile, we have Mars, 95.3% CO2, 2.7% nitrogen, and 1.6% argon. Again, no oxygen. Why? It turns out oxygen is extremely reactive. It doesn't like to just sit around by itself. It wants to form bonds with other things. It wants to be CO2, H2O, COOH, and all sorts of other fun molecules, but not the stuff that we want to breathe. So that's a problem. Oxygen's reactive, and we need to be able to free it up somehow, and the only way we're going to do that is through this wonderful thing called photosynthesis. The problem is, it took millions of years to do it on Earth. And that's not from the time life started, it's from the time that organisms first developed the ability to create photosynthesis to the time that we had an oxygen-rich atmosphere to the level that we would be able to breathe it. That's converting an entire planet's atmosphere. It takes hundreds of millions of years. So we have to ask, as the star grows, will a planet stay in that habitable zone long enough to convert an atmosphere? Well, we can take a look at that. Let's look at some other considerations first. So obviously the question from that is, we want a star to evolve slowly, which means it's going to be low mass so the planet can stay in it long enough. Other things, though, is we want, like we said, a breathable atmosphere, which is affected by photosynthesis, but to get photosynthesis, we actually want some CO2. So we need CO2, but CO2 can also be removed from the atmosphere, just like oxygen can. CO2 is much more stable, so it'll stick around longer, but it gets pulled out by things like silicate weathering, which means it gets locked up in rocks. Okay. So you take too long, you'll not have the CO2, but if you go too slow, you won't have the oxygen. We are in a really bad catch-22. Can we catch the curve? Probably not, unfortunately. So here's our summary. And there was a paper done in 2008, it was recently published last year, and basically what it said is the amount of time it's going to take for a planet with a mass similar to the Earth to lose all of its CO2 without something really funny happening is only about 6 to 7 billion years. So we don't need to worry about the sun eating us, we need to worry about running out of CO2 on the Earth for the plants to photosynthesize so we can breathe. That's a problem. So the other thing we need to do is just find more CO2, and fortunately there are huge amounts of CO2 just floating around the solar system. Ta-da! I found a mountain of CO2. Comets are about 80% CO, so carbon monoxide, and CO2. take that, smash it into the planet you want to live on later, and now you've got it ready to be able to do photosynthesis. So do that shortly before you have the planet entering the habitable zone. Seed it with some sort of Carl Sagan-esque photosynthesizing organisms, and by the time the habitable zone gets there, you might have a couple 100 million years to be able to live on it. So this is one hell of an investment. I won't be around to see it, but if I really, really, really care about my great-great-great-great-great-great-grandchildren, it might be worth doing. So this is a long-term survival strategy, but not something you want to do in the general sense. So that's kind of the end of my talk for this year. If you have any questions, feel free to ask them. I always take suggestions for other years, but as I said kind of at the beginning, it's extremely, extremely hard to do this talk, because a lot of times it's hard to constrain the variables well enough to do that. Does anybody have any questions?
One thing.